All right, we'll cover now the remaining problems from our practice final exam. This morning we concluded at problem 13. We finished up problem 13. So this afternoon I'll start with problem 14 on the practice test. So let me bring that up on your screen again. Okay, so here's number 14. Okay, and let's read the problem and then go into StatCrunch and do our calculations. All right. Listed in the data table, and this little icon here is your data table. We saw that in one of the previous problems. These are amounts of strontium 90 in millibecquerels, or MBQ, per gram of calcium in a simple random sample of baby teeth obtained from residents in 2 cities. Assume that the 2 samples are independent random samples selected from normally distributed populations. Do not assume that the population standard deviations are equal. Use a 0.05 significance level to test the claim that the mean amount of strontium 90 from city number 1 residents is greater than the mean amount from city number 2 residents. Okay, so let's go ahead and look at the data. All right, now we can copy and paste this right into StatCrunch. All right, I'll show you that in a second here. Okay, now first problem, what are the null and the alternative? That comes right out of the wording of the problem. Now, of course, we know that the null hypothesis always contains the equality sign. So B and D are out of the running. So the correct answer is either A or C. Now, in order to determine whether it's A or C, we have to look at the claim from the wording in the problem. And the claim is that the mean amount of strontium 90 from city number 1 is greater than the mean amount from city number 2. Okay, so that clearly is a one-tailed, it's a right-tailed test. So the correct answer here is C. Okay, now we can go into StatCrunch. So we'll copy and paste our data right into StatCrunch. And here you see it copied and pasted right into StatCrunch here. Now, I won't go through the steps for the t-test. You know how to do that. T-stats, to sample with data. Fill in your action window with your columns. Select your correct significance level here, which is 0.05. And when you do all that and hit compute, here are your results. Okay, so your t-stat rounded to 2 decimal places is 1.52, and your p-value rounded to 3 decimal places is 0.075. So let's take those values, plug them into our answer here. That's correct. Now this one is the problematic child, right? Where we've put in the right p-value, but the program doesn't give us full credit because it's looking for an interval, like a p-value interval. Now that is discussed in your text. We didn't go over it I would not consider it as part of elementary statistics, but that's up to the author of the textbook. But I will give you full credit if you take your p-value in StatCrunch and give it the answer from StatCrunch. So I'll be reviewing each and every one of your problems to make sure that you get full credit for your test. Okay? So there you have 0.075. And now we can make a decision by comparing the 0.075 to the given significance level of 0.05 up here. Okay? And when the p-value is high, or at least higher than the significance level, then H naught will fly. Okay? So we fail to reject. We, in effect, accept H naught. And so C is our correct conclusion here. We fail to reject the null. Okay? And so the data doesn't provide sufficient evidence to support the claim that the amount of strontium 90 from city number 1 residents is greater. Okay, so this null up here is not rejected, so we can't conclude that mu1 is greater than mu2. Okay, all right. Here in number 15, we start the set of problems from linear regression. All right, and so let's go ahead and read the problem, and then using the wording and data from the problem, we can go into StatCrunch and do our regression. Or not. I believe in this one we don't actually have to go into StatCrunch. The prediction line has already been calculated for us. So let's discuss what the X and the Y variables are for this particular linear regression. Heights in centimeters and weights in kilograms are measured for 100 randomly selected adult males and range from heights of 130 to 190 centimeters and weights of 37 to 150 kilograms. Let the predictor variable X be the height, that's the first variable, and the other variable Y will be the weight, okay? And in this problem, the mean and the standard, the mean of the X values and the mean of the Y values is given here. We're also told that the correlation coefficient is 0.372. And in a null hypothesis where the population correlation coefficient rho is 0, we would reject that null hypothesis, which is an indication that we can fit a straight line. If rho were too close to 0, then there is no linear correlation. Basically, they're independent. All right, so doing all of that and calculating the regression line would give us the value, or would give us the regression equation, all right, y hat, the predicted value of y given an independent or a predictor variable x is y hat equal to negative 103 plus 101 plus 1.01 times x. So given that equation, we can predict a value of y hat given a value of x. Here, x is taken to be 165. All right. All right, so in this problem, we have heights and weights. We have our prediction line, y hat, So what I'm going to do is simply plug in this value 63.65 right into our regression line and calculate a value of y hat for the predictor value 63.65, sorry, 165 centimeters. That's our predicted value x, okay? So what I'll do is switch cameras here, and you'll be able to see. Okay, so in problem 15, here's our regression equation, right? And all we have to do is go ahead and find the value y hat for the predictor variable x equal to 165 centimeters. And when we go ahead and plug this into the calculator, we get a value of 63.65. All right. So let's go back to the test now. Plug in our answer of 63.65 kilograms, and we get our predicted value based on a value of x equal to 165. Okay, so I would consider this sort of a warm-up for what we're going to be doing now. Okay, number 16 is another regression problem where we'll look at the data here, and let's read the problem. Listed below are systolic blood pressure measurements in mmHg. Okay, I'm not sure about that abbreviation. It may mean millimeters. I'm not sure. That doesn't really make sense. Hemoglobin, mmHg, obtained from the same woman. Find the regression equation, letting the right arm blood pressure be the predictor, x variable. Find the best predicted systolic blood pressure in the left arm, given that the systolic blood pressure in the right arm is 80 mmHg, okay? And use a significance level of 0.05. All right. Okay, now let's go ahead and copy our data right into StatCrunch here. I believe it's already there. Let me check and see. Do I have the data there already? No, I guess I don't. Okay. Some of you might recognize this, these data sets here from previous worksheets. All right, so let's go ahead and copy and paste the data. Okay, or just we'll copy the data right into StatCrunch here. So let me go ahead and do the Command C there, and then paste it right into StatCrunch here. Okay, and here it is over here, all right? Okay, so our X data is right arm, our left data is left arm. And then we'll go into regression, simple linear. Okay, and now we'll select our right arm as our predictor, the left arm as the response. And notice that there's an option here for the prediction of Y. We didn't go through this notion of the prediction of Y in terms of an interval. Okay, so let me just show you what happens if we look at the problem here. Okay, what we want to do, like we did in the previous problem, is predict a value of Y given a value of X. And here, X is going to be 80. And some of you are saying, oh, well, why don't we just, like we did in problem 15, why don't we just stick the 80 here for X and calculate the corresponding value for Y hat? Okay, so we could do that, all right, and let's see what we get here. Okay, first of all, let's calculate the regression equation back in StatCrunch. And just for fun here, I'm going to put in a value there of 80 systolic. Okay, so there's 80. We'll come back to that in a second. Right now, we want to get our line. Okay, and here's the equation for our regression line. Okay. All right. Now let's look at the scatter plot as well. Okay. We don't have a lot of data here, right? We've just got the 5 paired values, and here you see them plotted, and then here you see the regression line. Okay. All right. Let's go back to the. Let's go back to our results here. Look at our regression line, look at our correlation coefficient, and here we see the equation left arm 61.2 plus about 1.05 times X, okay, where X is the right arm systolic and Y is the left arm, okay? All right, so let's put that in our test here. 61.2 and 1.1. We're rounding to 1 decimal place. So again, let's stare at these results again. 61.2 and 1.1. Okay, so if you round to 1 decimal place, those are the values you get. The program likes those values. And now, if we go ahead, as I said, as we did in number 15, we plug in the 80 up here into our equation, and we return a value of 157.6, but the explanation here is that, let's see, there's a notion of a prediction interval. And this is discussed in, I believe, in section 10.3. We didn't get that far. So again, when I check your answers here, if I see that red triangle, then I'm going to go ahead and let's see. So let's see, let me show you the calculation here. So we're going to do we'll do a calculation here using our equation for 145 or for 80, right? Okay, so we'll type in, we'll calculate 61.2 plus 1.1 times the 80, which is our predictor. Okay. All right. And notice that 157.6, here's the let's go to the camera here. All right. Okay, there you see the calculation from the problem there, and the equation for the line here is 61.2 plus 1.1 times 80, and that gives you a value of 149.2. Okay. All right. Okay. So the predicted systolic pressure given here, 157.6. So, you know, the answer that was given by the student was 145.2. We calculated 149.2. I would consider the 149.2 the correct answer. Simply, as we did in number 15, remember how we did 15, we inserted the 165 as X, we calculated Y hat, and we get a value of 63.65. Okay, we're doing the same thing in number 16. If we're given the systolic blood pressure in the right arm is 80, we substitute 80 into this equation, and we get, again, 149.2. Okay, 61.2 times the value, the slope of the line, 1.1, times the given right arm systolic pressure of 80, and you get 149.2. All right. Okay. All right. Let's finish up this problem here. Okay. All right, so that's the regression line and estimating the y hat for a given value of x. Here x is given to be 80, and we get 149.2. Okay. All right. Okay, here is our next problem. And let's read the problem. The data show the bug chirps per minute at different temperatures. Find the regression equation, letting the first variable be the independent variable x, right? Find the best predicted temperature for a time when a bug is chirping at the rate of 3,000 chirps per minute. Use a significance level of 0.05. What is wrong with this predicted value? Now, before we start this, notice that 3,000 is a value for your x variable, which is outside the range of the data. So we would be doing something that's a little bit risky, known as a extrapolation. Okay, so we're taking a value of x, which is outside the range of the data. 3,000 is much bigger than 1,025. All right, so let's go ahead and copy and paste our data here into StatCrunch. Do the Command C. All right, and let's put it here. Okay, here's our data. All right, and now we can go ahead and do the linear regression. Our x variable is chirps in 1 minute, and the temperature is our y variable here. All right, and now we'll go ahead and do the prediction here. Okay. All right. So let's go ahead and get our t-stat, our p-value, simple linear regression. This is what we really want, is this. Okay. Let's look at the scatter plot here. That's a pretty nice fit, isn't it? And that's corroborated by the calculation of the correlation coefficient here. Very high value, very close to 1. Okay. So let's run with that. Here's our values here now. And in this problem, we get the line, and so here's our line here. Temperature is 33, almost 34, plus 0.046 times chirps in 1 minute. Okay, so let's go back to our test. All right, and here's our regression line. Okay, and again, a prediction interval for the y-intercept for this line, this simple line here, is given to you. The correct answer, it says, is 34 plus and minus 0.01. Okay, I would give you full credit for a value of 34, right? And then the slope of the line from StatCrunch is about 0.93. Sorry, looking in the wrong spot here. 0.046. So there's our slope. And well, we've got 4 decimal places there, sorry. So here's 4 decimal places. Okay. And we're good. Okay. So that's the correct answer. Y hat is 34 plus 0.0461 times X. Okay. All right, now, if we were to calculate a Y for an X value of 3,000, let's do that calculation now. So let's go ahead. Let me put it into the calculator here. So I'm going to type in 34. I'll show you this in a second. 34 plus 0.0461 times X, and X is given to us to be 3,000, right? And let's calculate that. I'll show you the result here. So let's go to our camera. And here's our result. Okay. Why it's a little fuzzy, I don't know. Well, I don't know if that helps or not. Okay, there you see the 34 plus, that's the y-intercept, plus the slope times the given X value of 3,000, and you get out a result of 172.3 degrees Fahrenheit. Okay, so obviously by extrapolating outside the range, we get a fairly incredible value in temperature of 172 degrees. So the danger in extrapolating is that you may get specious or misleading answers. So you have to be careful when you do regression to go ahead and use data within the range of the predictor range. Okay, this is 3,000 is way outside, and so we don't get sensible answers in that case. Okay, all right. So let's go back to our share. If I can find it. Okay. Okay, so here's our problem. And what did we see there when we got 3,000, when we let X be 3,000? We get this very large value, which is probably not a credible value, okay? And so if we look at these four choices here, C is the correct choice. It's unrealistically high, the value, and that's because the value 3,000 is way outside the range of the X values here. Okay. All right, so let's go to 18 now. And here we have the next problem. And we've seen this problem before on the worksheets. So let's read the problem. Find a regression equation letting the first variable be the predictor variable, X. Find the best predicted Nobel laureate rate for a country that has 78.9 internet users per 100 people. Okay, so then we'll come back and answer the question, how does it compare to the country's actual Nobel laureate rate of 1.1 per 10 million people? All right. Okay, so let's go ahead, open up the data set, copy and paste it into StatCrunch. Okay. And we'll put it here. Okay, so here we have our data. And now we can do the linear regression. So we'll go to regression here under stat, choose simple linear, and now fill in the action window. Our Y variable will be internet users per 100. Okay. Nobel laureates is the Y variable, the predicted variable or the response. And then we'll look at, we won't look at the confidence intervals here, okay? Here we have the intercept and slope. We didn't study this in class, so we won't choose these, all right? And we'll go ahead and compute. Let's just check confidence intervals and see what we get. Okay, so here we have our results. And okay, and for 95%, you see you get interval estimates of the y-intercept and the slope. Here you see them here, okay? All right, in the meantime, the equation of the regression line is given here, okay? So we're going to take that equation and run with it. We'll go in here. All right, and there it is. So let's go ahead, see what we get here. Okay, negative 23.1 plus 0.45 times internet users per 100. Okay, so our regression line is given there. And now let's see how that stacks up. Here we get negative 23.1. We round the intercept to 1 decimal place and then round the slope to 3 decimal places, and we get the 0.454. Okay. Now, if we used the instead the prediction intervals, we would get these values here. But I'm not using those. I'm using the values straight out of the line. And I'll give you full credit if you respond with these answers here. Even if you see the red triangles and you've done everything right, you'll get full credit in my book using these two values here, okay? All right. And then let's go back to, okay, the question up here, how does it compare to the country's actual Nobel laureate rate of 1.1 per 10 million people? Okay, all right. And oh, by the way, we have another problem here for this one. How does it compare the best predicted number of Nobel laureates? Okay, when the number of internet users per 100 is 78.9. Okay, again, if you did that in the calculator, let's do that one on the calculator. So we'll take our equation, negative 23.1489 plus 0.4542, and then we'll multiply that by 78.9. Okay, and let's see if I did this correctly. Oh, I'm sorry, I've got something in there. Let me do this. Negative 23.1489 plus 0.4542 times a value of 78.9, and that's 12.6874. And let me show you that calculation again. Okay, there you see. Oops, sorry. Okay, there you see the value of 12.68748. Okay, and when we go back to the sorry, let me go back to our test here. All right, here's our test again. And if we were to round 12.68748 to one decimal place, we would get 12.7. Okay. All right, and then finally, how does it compare to the country's actual Nobel laureate rate of 1.1 per 10 million people? Okay. Well, 12.7 here is a lot smaller. Well, it's a lot greater. Okay, 12.7 per 100 is a lot greater than the actual rate of 1.1 per 10 million people. Okay. And again, when we look at the data here, 78.9 gives us 12.7, right? And so you see that there's a big discrepancy between the 12.7, all right, and it really is not, you know, 1 point, here it is, 78.9 per 100. If you were to divide, you know, if you were to look at this and try and compare this with, all right, here, 1.1, okay. And it's the actual rate here is, turns out it's not actually very close. All right, and why is that? Okay, and then finally, if we were to look at the scatter plot for the data, notice that for a value of around here in this problem, we're looking at the number of internet users see here, the number of internet users per 100 is 78.9. Okay, now the line is predicting about 12.7. But when we go back to the graph here, we see that, you know, there's a little bit of a discrepancy because of this large residual here. Notice that around 79, you get this big jump, okay? So the line is predicting about here, 12.7. And so it's really probably, you know, there's some doubt as to whether it's giving us a good fit there around 79, because we've got these two extreme values. Notice that they're listed in pink. They're drawn in pink here. So it's not clear whether the 12.7 prediction is really a good prediction. It's probably not very close to the actual value. Okay. All right, let's keep moving on here. Right, let's go to 19. Okay. And here we have earthquakes, and the problem reads as follows: 50 match pairs of magnitude depth measurements randomly selected from 10,594 earthquakes recorded in 1 year from a location in Southern California. Okay. All right. Find the best predicted depth of an earthquake with a magnitude of 1.1. Okay. So let's go back to the data here. All right. And put it into our spreadsheet. Okay. Let's go into StatCrunch. And paste it here. Okay, so here's our data. And let's go ahead and do the linear regression. Okay. So our predictor variable is magnitude. Our response variable is depth. Okay. And now let's go ahead and compute the regression. Here's the data. Look at this. It's doing its best, isn't it? Okay, this scatter plot doesn't look very linear, does it? Okay. The correlation coefficient is not large, but certainly, you know, it's different from 0. Okay. And so here we get the regression line here. Okay. And so let's go ahead and take those results and work with those results. All right. And then we can use it to predict a value of y given x. Okay. All right, so let's take our values from StatCrunch. round it to 1 decimal place, 8.4, all right, for the intercept, and about 1.2 for the slope. Okay, so let's put that into our test. 8.4, 1.2, and those are correct. And then substitute a value of 1.1 into this equation here. Okay, so we're going to take our value 1.1 as our predictor, and we'll calculate y hat. So let's calculate 8.4 plus 1.2 times the 1.1, and that gives us a value of 9.72. Okay, and again, the 9.72 would be a valid answer. Okay, a third of a point was taken off. I would readjust that and give you a full point. Okay, all right. Okay, now now we're going to get into tests of independence and contingency tables here, and let's go ahead and work these problems. Okay, so here is the problem statement. Conduct the hypothesis test and provide the test statistic and the critical value and state the conclusion. So in this problem, it says a person randomly selected 100 checks and recorded the cents portions of those checks. The table below lists those cents portions categorized according to the indicated values. Use a 0.025 significance level to test the claim that the 4 categories are equally likely. Okay. All right. And the person expected that many checks for the whole dollar amounts would result in disproportionately high frequency for the first category. The first category are 0 to 24 cents. All right. Let's look at the results for the goodness of fit test here. Okay, so let's go into StatCrunch. Well, let's see. Let's go ahead and copy and paste this data right into StatCrunch. Put it here. Okay, so here's our data. All right. And now let's do the goodness of fit. And the problem statement is the following. Let's test that the 4 categories are equally likely at the 0.025 significance level. Okay, so we'll go to okay, trying to get this. Okay, so let's go to our goodness of fit here. We know that's going to be a chi-square test from chapter 11. And we'll go ahead and look at our observed counts, right? So that's number here. And then we'll assume our test is going to be that they're equally likely, or that all cells in equal proportion of 25% per cell. Okay, so let's compute our test statistics for the goodness of fit. And in this particular problem, our chi-square statistic is 42.96, pretty large chi-square value, indicating that it's probably not a good fit. And the corresponding p-value is very small, very close to 0. Okay. Now let's take those results and answer the questions in our problem. We see that the test statistic was 42.96, right, from our test. And the critical value now, since this has k equal to 4 categories, the degrees of freedom for the test is k minus 1, or 3. Okay. And we'll put, remember, this is a right-tailed test, so we'll put alpha equal to 0.025 area there in the right tail, and that'll give us our critical value for the test. So we'll go to stat calculators. We'll choose the chi-square distribution. And we said the degrees of freedom, k minus 1, is 3. And we'll change this. We'll put a 0.025 here on the right side. That's the area specified in the right tail. We'll change that to greater than or equal to. And there we get a critical value of 9.3484, rounded to 4 decimal places. Okay, so we go back here. It says round to 3, so it would be 9.348. Okay, round your critical value here to 9.348, and that's going to be our critical value. And then remember here, what is our conclusion? Well, p-value is very small, and another way to decide equivalently is that our test statistic is way to the right of the critical value. Okay, so that would put us in the rejection region. And so we would reject the null hypothesis of a good fit. And in fact, the data support the rejection of the claim that the 4 categories are equally likely. All right. And notice the results support the expectation that the frequency for the first category is disproportionately high. Okay. Notice that in the first category, you've got 53 of the 100 checks, more than half, have cents in the category 0 to 24. Okay. Let's read this problem, number 21. Conduct the hypothesis test and provide the test statistic and the critical value and state the conclusion. A company claims that its packages of 100 candies are distributed with the following color percentages: 15% red, 20% orange, and so on. Okay, here's the sample data. Okay, there's our sample data there. Okay, use the sample data to test the claim that the color distribution is as claimed. Okay, all right. So let's compare the candy counts here with these given percentages up here 15% red, 20% orange, and so on. Okay, so these are the expected frequencies up here. These are the actual counts for the 6 different colors. So let's go ahead and copy and paste these. Go into StatCrunch. Let's put the data right up here. Okay. And now we can do a goodness of fit test. All right. And let's go to goodness of fit, chi-square, and our observed is right here. And that, of course, is the number in the package. And then our expected is given in the color column. Okay. And remember what the percentages were. Okay, so let's go ahead and fill in the correct percentages. If we multiply by 100, let's see. Let's go ahead and put expected here. Okay, and let's see, for our expected values, we have to pick out, let's see, out of 100 we would expect 15% or 15. Okay, so there we have our expected 15, 20, 14, 13, 22, and 16. Okay, so let's go ahead and fill in those expected values. So 15, $15, $20, $14, okay, $13, $22, and $16. Okay, and now we can do our goodness of fit. We'll select our expected values here, and now compute our statistics. And here we see a chi-square there of about 5.45, the p-value of 0.3627. Okay. 15, 20, 14, 13, 22, and 16. Okay. And there we see the test statistic. Our test statistic here, 5.46, and our p-value of 0.3627. Pretty good p-value there, right? Okay, so let's go ahead, put in 5.46, and here student answered 16.52, and the answer would be 5.46 plus or minus 0.01. Okay, again, the 5.46, I would consider that as correct. Okay, and so let's calculate the critical value. remember we have K colors here. So the degrees of freedom for the goodness of fit is K minus 1, which is 5. So let's go into our calculator for chi-square. Here is chi-square. And our degrees of freedom, we said, is 5. Okay. And our area in the right tail is given to be 0.01. Okay, so let's put 0.01 in the tail. And now compute. That has to be reversed there. Okay, and we get 15. All right. So here, let's see. 15.08. That gives us a probability of 0.01 in the tail. Okay. And 15.086. Here it is, rounded to 3 places. 15.086 from our StatCrunch work. And student answered 11.071. That's incorrect. All right. Okay, and so the test statistic falls to the left of this critical value, right? And we saw from StatCrunch that the probability value was high. It's 0.3627, and therefore p-value is high, h0 will fly, and we can say, in fact, that there is a good fit. And here, we do not reject h0. The data do not provide sufficient evidence to warrant rejection of the claim that the color distribution is as claimed. Okay, so looking at this, looking at these observed values here compared to the expected values, it's really not off by that much. At least the data is not significant, does not back up the claim. So we're left with the null hypothesis that you have a good fit here. Okay. All right. Keep churning here. All right. The next problem states the following: the table below. Let's look at the table. Here's our table. And the table shows you a contingency table here. And we're going to do a test of independence between the two column labels and the row labels here. And the row depict a polygraph test, and polytest comes up as the subject lied versus polytest subject did not lie. And then you have the actual truth over here above the columns. No, did not lie, and yes, lied. Okay. So let's just inspect the data here. So in fact, the polygraph, okay, noted that there were 9 instances where the subject actually did not lie, but the poly said the subject lied. There were 9 of those. Okay. Poly was correct for 32 of the cases. And then in the second row, how well did the poly do when the subject did not lie? Poly says their subject did not lie. In fact, the subject did not lie. for 28 of those cases. And in 13 of those cases, the poly was incorrect. Okay? All right, so let's set up the test for independence. Is poly result independent of the truth? Okay, so we can state that as follows. Whether a subject lies is independent of the polygraph test indication. And then the alternative, the correct alternative would be whether a subject lies is not independent, okay, of the poly test indication, okay? So let's go into our contingency table in StatCrunch. We know that that's under applets. So here's the contingency table. And we'll type in our row labels. Okay, and let's see. I don't think I have, let me remove some of these results here. Let's set up some room for our data table here. Okay, so well, I'm sorry. Let's go ahead and type in the row labels and the column labels. So the row labels here are the following. Okay, and let's see, how are we going to define our labels here? Okay, so let's take our, let's see, let's use the following labels here. Okay, we have to be a little creative when we do this. Okay, so I'm going to type in the two row labels as the poly indication. Okay, so poly in this first row, the poly indicated a lie, and then in the second row, the poly indicates did not lie. Okay, and let's just write that as no lie. Let me typo there. Okay, and then the columns are the truth labels, where in fact no lie, subject did not lie. Okay, and then the subject in fact did lie. Okay. Okay, so these are our descriptions of the poly indicator. First row is poly indicates lie. Second row, poly indicates did not lie. And then in the truth columns, first column is the subject did not lie. And in the second column, the subject did lie. Okay, so let's go ahead and populate our table here with our data. And there we had, let me fill in the data, 9, 32 in the first row. And in the second row, we have 28 and 13. Okay. All right, and now let's compute the test statistic for the test for independence. And we get a test statistic of 17.7790, rounded to 4 places. Very small p-value. Okay, So, and now we're going to go back to our test. All right. And let's go ahead and take our value there, the test value for the chi-square test of independence. Okay, here it is. And then we can also calculate the critical value for the chi-square test using our chi-square distribution and the specified level of significance here. Okay, and that's equal to 0.05. So let's go ahead and calculate our chi-square critical value. All right. Now the degrees of freedom are going to be R minus 1 times C minus 1. Now both R and C are 2, so we get a 1 is the degrees of freedom. We'll put 0.05 area in the rejection region, and then we'll change that to greater than or equal to, and that'll give us a critical value of 3.8415, rounded to 4 decimal places. So let's go back to the test. And okay. By the way, the p-value for that critical value here, we saw to be very close to 0. Okay, so that's our p-value there. And now let's go to the test and put in our p-value. P-value is low, so H naught is a no-go, so we're going to reject. And so there is sufficient evidence to warrant the claim that whether a subject lies is independent, okay, of the polygraph test indication. Okay, so we'll reject the notion of independence, and appears that the polygraph is working correctly. Okay. All right. Okay. So let's go into our next problem here. Okay. Let's move on here. We're making progress. So I'll read the problem again, and we'll go through the exercise here. Okay, the table below summarizes data from a survey of a sample of women using a 0.01 significance level and assuming that the sample sizes of 700 men and 300 women are predetermined. Test the claim that the proportions of agree-disagree responses are the same for subjects interviewed by men and subjects interviewed by women. Does it appear that the gender of the interviewer affected the responses of women? Okay, so let's go ahead and look at our data here, our contingency table. All right, and we'll go ahead and use our chi-square test here, and we'll look at the proportions of agree-disagree and our null hypothesis. The correct null hypothesis is A, the proportions of agree-disagree responses are the same for the subject interviewed by men and women. Let's see, let me read that again. The proportions of agree-disagree responses are the same for the subject interviewed by men and the subjects interviewed by women. Okay, So what we're going to do is sort of a test of homogeneity here. It's not really a test for independence. So we'll use the test of homogeneity in StatCrunch. I'll go ahead and choose, let me hide these results here. And now we'll go to our contingency table under applets. And we'll go ahead and type in our row labels. And I'll type them this way. Okay, for the first row, we'll type it as W agree. And then in the second row, we'll label it as W disagree. And then we'll label the two columns simply the interviewer, gender, male and female. Okay, and now we'll compute and we'll fill in our table with the data given to us in the exercise. So first row, first column is 442. Second row, first column is 258. First row, second column is 256. Oh wait, I have a typo here, I'm sorry. Okay, that looks better. Okay, and then the last cell, last column, last row has a value of 44. Okay, so there's our data. And let's compute the chi-square test of homogeneity. And here are the statistics. Okay. And there you see the chi-square statistic is about 49, p-value close to 0. So let's take that back to our problem here. All right. And let's go ahead and choose the correct hypotheses here. Student selected B. It's not a test for independence. It's a test of a goodness or a test for homogeneity where the proportions of agree disagree are the same for the subjects interviewed by men and the subjects interviewed by women. Okay, so let's go ahead and compute the test statistic, which we just did, and we got a value of about 49. Okay. And we have to round it to 3 places. So if we round this to 3 places, we get 49.056. All right. Okay, that's the correct answer. And to find the critical value, we'll go to the chi-square calculator again. Okay. Here's our chi-square calculator. And to calculate the degrees of freedom, R is 2, C is 2, and R minus 1 times C minus 1 is 1. Okay. And in this problem, our significance level alpha is 0.01, which means we're going to have 0.99 area sorry, 0.01 area in the tail, in the right tail. We have to change that to greater than or equal to. And there we get the critical value of about 6.63. Okay, 5 if we round to 3 places there. Okay, so let's go back to our, our problem. And there's our critical value, chi-squared with 1 degree of freedom, leaving 0.01 area in the right tail, and that's 6.635 rounded to 3 places. Okay, 6.635. Okay, and now we can work this problem. Okay, we've got our test of homogeneity there. And now, because of the large chi-squared test statistic here, certainly much larger than our critical value, we conclude that we reject H naught. And in fact, the data in this table here provides sufficient evidence to warrant rejection of the claim that the proportions of agree-disagree responses are the same for subjects interviewed by men and the subjects interviewed by women. It appears that the gender of the interviewer affected the responses of women. Okay, so we reject the claim, and we see that gender does play a role in the responses of women. Okay, all right. Okay. All right, now we're looking at smokers and seatbelt users. Let's read the problem. A study of seatbelt users and non-users yielded the randomly selected data summarized in the accompanying table. Let's go ahead and look at the data now. Here's our contingency table. And across the columns, we have the categories of number of cigarettes smoked per day. And then the column labels refer to the seatbelt use. The first row label is wear seat belts. The second row label is don't wear seat belts. Okay. And the categories of cigarettes are 0 cigarettes smoked per day, 1 to 14, 15 to 34, 35 and over. All right, so let's go in StatCrunch, set up the contingency table here. Okay, let's hide these results. Go into our applets list. And now let's select our labels here. All right. And let me use these labels here. First row label will be, we'll call it wear seatbelt. I'll abbreviate seatbelt with SB. And then the second row label will simply be, let's see, do not wear seatbelt. We'll just leave it as do not, okay? And then the columns, we can label those by the number of cigarettes smoked per day, 0, 1 through 14, okay. Let's see, 15 through 34, and 35 or more, okay? So let's say
well, let's just make this like, we'll denote it as greater than 34. So those are the 4 categories of quantity of smoking. And now let's fill in our data in this table. Okay. So the first row is 155, 10, 46, and 6. Okay. Second row values would be 153, 18, 50, and 13. Okay, let's compute to get our test value and p-value. P-value is kind of low there. Look at the p-value, pretty healthy, 0.2205, all right? And so now let's go back to our exercise here, all right? And let's pick out the correct set of hypotheses here, and notice that B fits the bill. Okay, test for independence based on seatbelt use and cigarette use. Okay, so the null hypothesis would be the amount of smoking is independent of seatbelt use versus the amount of smoking is not independent of seatbelt use. Here's our test statistic. We got a value of 4.4 if you round it to 1 decimal place. Okay. Round to 3 decimal places, we would get 4.410 as our test statistic rounded to 3 decimal places. All right. And again, there is a correct answer here given as an interval. All right. But again, I would, let's see, the student answered 4.1, and then the correct answer I would accept as what we've just derived in StatCrunch here. To 3 decimal places, this would be 4.410. Okay? So no credit taken off if you report the result 4.410 as given to you in StatCrunch here. All right? Okay, and now we can make our decision. Okay, the p-value here, we round to 3 decimal places, and the p-value is 0.221 if we round to 3 places, 0.221, okay? All right, and then high p-value means that we do not reject the null hypothesis. Okay, so we favor H naught, so there's not sufficient evidence to reject the claim that the amount of smoking is independent of seatbelt use, okay? And the plausible theory is that people who smoke are less concerned about their health and safety, and therefore less inclined to wear seatbelts. Well, the data don't support that claim, okay? So that theory is not supported by the sample data. Very good, okay? Okay, let's go on to number 25. A poll was conducted to investigate opinions about global warming. The respondents who answered yes, when asked if there is asked if there is solid evidence that the Earth is getting warmer, were then asked to select a cause of global warming. The results are given in the accompanying data table. Use a 0.05 significance level to test the claim that the sex of the respondent is independent of the choice for the cause of global warming. Do men and women appear to agree, or is there a substantial difference? And here you see the breakdown. Row labels are gender, and the column labels here are the different causes that might be attributed to global warming: human activity, natural patterns, and then this last category, don't know. All right. And fairly close agreement between males and females in terms of a cause, a human activity. A little difference in natural patterns, and similar results in the don't know category here. All right. And so let's identify the null and the alternative first. So the gender, the sex of the respondent, and the choice for the cause of global warming are independent. So there's your null, independence between gender and the cause, and versus the alternative that these two characteristics, gender and choice for the cause, are dependent. Okay, so let's go into StatCrunch, set up our contingency table for the test of independence. Okay, let's go ahead and hide that result. So under applets, we choose contingency table as usual, and then we'll select our row labels, male, female. And our column labels are the cause. So let's label those human, natural, and don't know, DN. Okay? All right, now let's complete the table with our data, our given data here. So the first row here, let me type in the values: 310, 137, and 62. The second row, 308, 166, and 67. Okay, now we'll hit compute. And there we have our statistics here. Chi-square is about 2, and a high p-value, 0.3674. Okay, so let's go back to the exercise. All right, we've got our 2 hypotheses squared away. And as we saw from StatCrunch, our test statistic is about 2. And it says round to 3 places. Okay, so if we get about, well, I would get about 2.002. Okay, and see the, don't know if it would like 2.002, but 2.003 is awfully close. Okay, and now let's go back in, find the critical value for the test. And now we've got 2 rows and 3 columns. So our degrees of freedom for the test for independence is R minus 1 times C minus 1. So that's 1 times 2, or 2. Okay? So our degrees of freedom is calculated to be 2. And now let's go into our calculator for chi-square. That's under stats, calculators, chi-square. And R minus 1 times C minus 1 is 2. And our significance level here is 0.05, 0.05. It's in the right tail. And we get our critical value of about 6. Okay? Or rounded to 3 places, it would be 5.991. So let's go back to the exercise, type in our critical value, and notice that the test statistic falls well inside the acceptance region, so we fail to reject, and our conclusion is that there is not sufficient evidence to warrant rejection of the claim that the sex of the respondent is independent of the choice for the cause of global warming. And in fact, we see that men and women appear to agree based on that conclusion. Okay. All right, we're getting close to the end here. Okay, number 26. Okay, number 26 here. Let's read the problem and then we'll decide which test we're going to use. Samples of pages were randomly selected from 3 different novels. The Flesch Reading Ease scores were obtained from each page, and the calculator results from ANOVA are given below. Okay, so let's click on the icon here and take a look at these results here and see if we understand what's going on here. Okay, so notice that in these results, we have the F statistic here for the test that the 3 mean scores for the randomly selected novels, okay, the sample pages taken from 3 different novels. So our null hypothesis is that the scores are the same across the 3 different novels. And the alternative would be that 1 or more of these scores are different, okay? So notice that in the results, based on the calculator, the TI-8384 calculator, notice that you get 2 things to notice here. F is reasonably large and P is small, okay? It's very close to 10 to the minus 4, all right? And we've got degrees of freedom 2 and 30, all right? So those are the results that are given from the calculation. And again, because F, like chi-square, is a right tail test, we see that the p-value is very small, close to 0. So we would reject. the null hypothesis, and we would conclude that the data provides sufficient evidence to warrant rejection of the claim that the three books have the same mean flush reading E score. Okay. All right. Okay, and let's look at the next problem here. A sample of colored candies was obtained to determine the weights of different colors. The ANOVA table is shown below. And here we have some assumptions. It is known that the population distributions are approximately normal and the variances do not differ greatly. Use a 0.025 significance level to test the claim that the mean weight of different colored candies is the same. And then finally, if the candy maker wants the different colored populations to have the same weight, do these results suggest that the company has a problem requiring corrective action? Okay, so here are the statistics that we really need, right? The test stat F is 4.7321. The critical value, based on the degrees of freedom in the numerator and the denominator, okay, is 2.5667, and the p-value is small. It's 0.0003. Okay, our alpha is 0.025, and certainly p is less than alpha. So that would indicate that we would reject. Okay. Okay, so should the null hypothesis that all the colors have the same mean weight be rejected? Yes, that's B, because the p-value is less than the significance level. Does the company have a problem requiring corrective action? Okay, and since we've rejected the null that the mean weights are all the same across colors, we would respond yes, because it is likely that the candies do not have equal mean weights. Okay, all right. So that's number 27, ANOVA. Okay, 28 reads the following. A certain statistics instructor participates in triathlons. This looks like one of our worksheet problems. The accompanying table lists times in minutes and seconds he recorded while riding a bicycle for 5 laps through each mile of a 3-mile loop. Okay. Use a 0.05 significance level to test the claim that it takes the same time to ride each of the miles. Does one of the miles appear to have a hill? Okay, let's look at the data. I believe it's the same data from the worksheet. Okay, let's set up the null and the alternative. Remember, for ANOVA, the null is always that the means across the different populations are the same, and the alternative is that at least one of the 3 population means is different from the others. Okay, so let's compute the F statistic using the data from the table and its corresponding p-value, and then we can make the conclusion for this particular hypothesis test. All right. Okay, now I think that I have the data already stored in StatCrunch. Let me double check that. We've got a lot of data in here, don't we? Okay, so we're looking at, oh gosh, I don't see it. Okay, so we're just going to have to type it in. All right. Okay, let me go over to the right side of the spreadsheet, and we'll go ahead and type the data in. Okay, so let me first type in some headers for the data columns here. Okay, so we'll have mile 1, mile 2, and mile 3. Okay, and now like I did in the worksheet, I'll convert these to seconds. And so, so let's take our data here. Okay, and notice that 316 is 180 plus 16, so that would be 196. So let me just type in the data and convert them into seconds. You could use decimals as well, okay? But I found it easier just to use the seconds. So let's go mile 1. The values are 196, 205, 203, I'm going to check one other thing here. Let's go back to the problem. Okay, and let's see. I'm not sure how StatCrunch would treat this data. Let's go ahead and give it a shot. Let's go ahead and copy and paste this data. Mile 1, mile 1, mile 2, mile 2 seconds. Yeah, it looks like it's creating different columns for the minutes and the seconds. Well, let's just give it a shot and see what it looks like. Otherwise, we'll move forward with the seconds there. Okay, so Command C, and then let's attempt to let's put it up here. Yeah, that's not what we want, is it? Okay, because it's separating off the minutes and seconds here and giving us 6 columns. So let me nix this and continue with the seconds data here, like we did in the worksheet. Okay, so our next value for mile 1 is 201. Okay, and the last value is 200. For mile 2, the 5 data values are 198, 202, okay, and 200, 197, and 198. And then finally for mile 3, it's 210, 208, 212, let's see, I'm sorry, mile 3, 213. Let me move these down a notch. Okay, I mistyped the data here. Mile 3, 213 is the first data point. 210, 208, 212, and 209. Okay, now this looks right. Okay, so those are our three populations, our samples, our three samples. And now let's do the one-way analysis of variance. Okay. All right, so let's pick off the ANOVA here, one way, and we'll select the last, oops. Okay, we want this column. Okay, we want these three columns, and our significance level is 0.95. Okay. And let's do our F-test here. Okay. All right, here's our ANOVA table showing the F statistic and the probability value. Okay, so let's go ahead and proceed with our solution here. Okay, and let's go ahead and first determine, let me keep this up. Okay. Let's determine the null. The null is that the three population means are equal against the alternative that at least one of the three population means is different from the others. The F-stat from our StatCrunch ANOVA rounded to 4 places is 28.0707. Okay, and the p-value is less than 0.0001. Okay, so if we round to 4, we get 28.0707, and the p-value is about 0.0001. Okay, and obviously we're going to reject, so it's either B or C. And now when we reject, the proper verbiage is that there is sufficient evidence to warrant rejection of the claim that the 3 different miles have the same mean ride time. So B is the correct conclusion there for that test. Okay. And if you look at the data for mile 3, it does look to be times are a little higher, okay, over the loops there. And here are the means. Here are the means. Notice for mile, let's see, mile 1. Okay, mile 1, let's see. Okay. All right, let's see here. Let's see, did I did have the, the correct data. Let me, I see a discrepancy there because oh, I'm sorry. Yeah, here's the means, and you can see that for mile 3, there's a slightly higher mean. Not actually slightly higher, but in terms of seconds, it seems slight. But remember that it's not really the it's the means and the standard deviations. Okay, so this tells us that mile 3, because it's showing a higher mean here, may have some sort of a hill in it, which would slow down the mean is higher. Okay, and so the hill might speed up the guy, the triathlete. Okay, so there we would say that 3rd mile appears to take longer, and a reasonable explanation is that it has a hill. Okay, so slower times for mile 3 indicate that, in fact, you might have some sort of a hill there that might slow down the rider. Okay? Okay, we're getting to the end finally, number 29. Let's look at the table. All right, and let's read the problem as we, okay, here's our data. Okay, now this data shows the amount of nicotine in milligrams per cigarette in king size cigarettes, 100 millimeter menthol cigarettes, and 100 millimeter non-menthol cigarettes. The king size cigarettes are non-filtered, while the 100 millimeter menthol cigarettes and the 100 millimeters, okay, 100 millimeters non-menthol cigarettes are filtered, use a 0.05 significance level to test the claim that the three categories of cigarettes yield the same amount of nicotine. Okay? And then once we do that, we'll answer the question, given that only the king size cigarettes are not filtered, do the filters appear to make a difference? All right. So as usual, the ANOVA test is that the three means in nicotine amounts, the three means are equal versus the alternative that at least one of the three population means is different from the others. Okay, so let's go ahead and let me just check and see if the data is already there. If it's not, we'll just copy and paste it in. Okay, I don't see it. Okay, let's just go ahead and copy it in. All right. Let's go out to the very right and go back to the problem. Oops. So here's our data. All right. And we'll go ahead and do the copy and paste. Okay, and so here's our data there in these last three columns here. Okay. All right, let's go ahead and do the one-way ANOVA now for this data. Way down at the bottom here. There's our three data sets, our three sample values there. Okay, and alpha is 0.05. So let's work that. Okay, and we compute our statistics for the data. And here is the key statistics here. We get a f-stat of about 5.667 with a fairly small p-value, less than 0.05, certainly 0.0088. Okay? All right, and degrees of freedom for the numerator and the denominator are given there. And let's go ahead now and solve the problem. Okay, all right, so here's the F statistic. Compare that with what we got here. And let's see, we have to round this, I think, to 4 decimal places, 5.6670. Okay? All right, so there's our F statistic 5.6670, right? Okay, and the p-value rounded to 4 decimal places is 0.0088 from StatCrunch, and now I think we're pretty good to go here. All right. Okay, so in StatCrunch we calculated both the f-stat and its p-value, and the p-value is low, h-naught is a no-go. Okay, so we reject h-naught, that's a D here, and the correct wording is, there is sufficient evidence to warrant rejection of the claim that the 3 categories of cigarettes yield the same amount of nicotine. Okay, and we can say that since the king size cigarettes have the largest mean, the other 2 have lower nicotine values, it appears that the filters do make a difference. Okay, so that's a supposition. There's no analysis to back that up yet. All right, so we can just tell the client that it appears that the filters will make a difference. Okay, more studies need to be done to really nail that down. Okay, and in the last problem here, we have the situation where, let's read it, the accompanying data, open the data set here, and there we have 4 categories here for the poplar weights. So the problem reads as such: the accompanying data are the weights in kilograms of poplar trees that were obtained from trees planted in a rich and moist region. The trees were given different treatments identified in the accompanying table. Also shown are partial results from the Bonferroni test with the sample data. Now, Bonferroni is not something that we studied in our worksheets, so I won't give you a problem on the final with any Bonferroni test, okay? But let's do the analysis of variance on the data that we're given up here. So the null again is that the mean weights are equal for the 4 treatments here. Well, the first treatment is the no treatment column, all right? So we have the no treatment versus the treated trees. And of course, the alternative is at least one of the 4 population means is different from the others. So let's go to the F test in StatCrunch. And let's go ahead and copy and paste the data. Okay. Put it here. Okay, so there's our data. And now we can do the one-way analysis of variance for these 4 means. Select off the columns down here. And now let's see, our level is for this problem it's 0.10. So let's change this in Tukey. Remember, the text uses this idea. Okay, and we'll compute and get our f-stat, okay, and our p-value here. All right, so there's our test using analysis of variance, okay? And now we'll take those values to answer our questions there. Okay. All right, so the test statistic given in StatCrunch rounded to 3 places, 2 or 3 places, 6.61, 6.61, rounded to 2 places, okay? And then the p-value rounded to 3 places is about 0.004, okay? And now let's finish it up, okay? And again, p-value is low, so H0 is a no-go. We reject H0. Furthermore, the correct way to say this is that the data do provide sufficient evidence to warrant rejection of the claim that the 4 different treatments yield the same polar weight. Okay? Now, we'll skip the rest of this. I won't give you a problem requiring the Bonferroni test. Some of you might be interested though, and you can read up in your textbook. One might want to understand the difference between the fertilizer versus the no treatment, or the irrigation versus the no treatment, and so on. Fertilizer and irrigation versus the no treatment. And Bonferroni gives you a way of doing that, okay? All right. Okay, so that concludes our practice test. And I'll make some announcements about the final. And so I'll put that in the announcements as well. Let's see, there was a request to post another practice test. Remember, for the midterm, you requested another practice test for the midterm. And so what I'll do is I'll go ahead and gin one up and post that in my lab. And again, these practice tests are not graded. They're just for you to prepare for your final, all right? So we'll have office hours on Thursday starting at 11:30, and we can go over any of these problems that you see here from 1 to 30, and I can go over the solutions with you again. But please, I'll go ahead and start the video. That'll take some time to gin up. And while that's ginning up, I'll compose a second practice test, okay? And then after I do that, I want to post some more comments in the announcements concerning the final. All right, so let me stop the recording here now, and we'll go ahead and post this to your announcements.